Okay, today, in your text for the last few days, you've started to read the information. You had a section review over humidity and condensation and evaporation, things like that. What we're going to do today is go through and look at those. The first thing you need to do is in your notebooks, I've got, I believe, 9 vocabulary words that we need to make sure that we know for sure and get those in. So what I've got is a presentation here, a PowerPoint. We're going to put it up here. It's not real dark because of the light, but you should be able to see it. And we're going to go through those words one at a time and make sure you understand each one of those. So copy it down as we go. First word, evaporation. Cooling process by which water is changed from the liquid form, which is water, to the gas form, which happens to be water vapor. Thinking about evaporation, we've talked about several possibilities or examples of evaporation. When we talked about oceans and we looked at principles of desalination, what was one principle that we used in desalination as far as evaporation goes? Somebody remember? Danny? Desalination. One method that used evaporation. Remember what that was?
The water evaporates and the salt stays.
Okay. Salt stays, the evaporation, the water rises to the top, runs down the side. You can collect that fresh water. Now, evaporation, this is the most important thing you need to know about evaporation is it's a cooling process. And we're going to do a little mini lab over here that's going to look at that in a little bit more detail and give you a better chance to understand that it's a cooling process. And what you're looking at basically is taking water from its liquid phase and putting it to its gas phase. And there are probably 50 different variables that can influence the rate of evaporation, and we'll talk about a few of those too. Is everybody at this? Okay. Other term, the two major ones, we're looking at evaporation, and this is the second one, condensation. Basically, you can say that these two are opposites. You take evaporation, you take water in the liquid form, and you transfer it into water in the gas form. Condensation is just the opposite, where you take water that is in the gaseous form and convert that into water into liquid form. Condensation, process in which gaseous water, which happens to be water vapor, is changed into a liquid form, which would be regular water. Anybody think they can give a good example of condensation? Or some time when they've experienced what they thought was condensation? Curtis?
Like dew, in the morning.
Okay, dew on the grass. If you happen to get up nice and early, and it depends on the environmental situation, and take off your socks and shoes and go running barefoot through the grass in the morning, your feet might get wet. That's from dew or water that was out of the atmosphere that has collected on the grass. That's one example. Another example of condensation? I'm sure you've all experienced this one. Nathan?
When, it's cold outside and you breathe on the window glass.
Okay, that's one. It's cold outside. You go up to a window itself and you breathe on the window. You have, every time you exhale carbon dioxide, other gases, as well as water vapor. The water vapor in your breath hits the window, it cools and collects, and that's condensation. Another one. Rod?
Like when you're cooking and the steam from the pan hits the lid.
Okay, that's one. If you're boiling something, cooking something, you take the lid and lift it up, and there's water that's collected. You take the lid and set it on the stove, and then you have water that runs everywhere. Another really good example you've all experienced.
If you have a cold glass of water, and then,
a picture from the book. Exactly. You take a cold glass of water, take it out, set it on a table or whatever, especially in summertime, and you come back, and then there is moisture all around the outside of it. I did this, we'll do it here in just a little bit. One time I was talking about condensation with these 4th grade kids, and I told them, here's a glass, it's got water on the outside. I want you to tell me how this got here. We need to come up with how it is. And I said, you can only tell me, or you can only ask me questions that end in yes and no. And we sat there for 45 minutes. They asked me questions. Mr. Knor, da-na-na-na-na. Yes. Mr. Knor, da-na-na-na-na. And I said, no. and when they finally came up with the reason why condensation takes place. Now, we know that condensation is water collecting on the outside of a cup. What I want to know is why. This is my question I posed to you now. TJ, what do you think? If I take this Pepsi can, and right now I can pick it up and feel it, and it's got water on the outside of it. Why does this have water on the outside of this Pepsi can?
It's like cooler on the inside and warmer on the outside, so it's like evaporating.
It's like evaporating? Okay, he's got some good points, and right off the bat, he's got pretty close. What do we know about two things? First of all, this Pepsi, is it warm or cold? It's cold. Okay. When you take, example, condensation, and you take water from a gas form, or like water vapor, and you try to turn that into water as a liquid form, what do you have to do to that water, or that water vapor? To get it to go from a gas to a liquid. It's the same thing you have to do to make it go from a liquid to a solid. Curtis?
You have to take the heat out of it to make it go from a gas form to a liquid form.
Okay, what's another way to say take the heat out of it? Cool it. If you cool water vapor, it turns into liquid. If you cool liquid, it turns into solid. Why do you think that the water vapor in the air is collecting on the outside of this Pepsi can? Because it's cooler. And what's that do to the air around the Pepsi can? It cools it, and the water vapor in that air around the Pepsi can cools and turns to water and collects on the outside of the Pepsi can. That's condensation. And there are 100 examples of that. Everybody got this? We'll talk more about this a little bit. Next one. Saturated. Term used to describe the air when it is at the limit for the amount of water vapor that it can hold. This one, you can use saturated to describe a great deal of things. The one we're looking at is the atmosphere. The air in the atmosphere will only hold a certain amount of water vapor. When it reaches the point where it loses its ability to hold water vapor, what does it do? Jim? It rains. Or you get a rapid temperature change, and then suddenly a cloud can't hold as much water vapor as it could before, and then it rains. Another thing to use to describe saturated. Nice dirty sponge here. Okay. Is this sponge saturated? Caleb? Why not?
Because there's no water in it.
Not much water in it. How could I saturate the sponge? Okay. Submerge it to a point where if I tried to mop up a spill or something with this, that it wouldn't pick anything else up. It's got all these nice little air pockets in here that trap the moisture or the water, and once it gets saturated, it can't hold anymore. And it gets to the point where it's saturated and hold it up, what will it probably do? It's going to drip. So it's only holding a certain amount of water, and eventually it's going to start giving some of that off. Other things you can describe as being saturated. A few days ago or last week, the soccer fields were saturated. We'd had so much rain for an extended period of time that it couldn't hold any more water. If ground gets to the point where it's saturated, what usually happens? Floods. The water can't go in the ground. It's got to run up on top and usually run downhill. It's like the video we watched last class period talking about those canyons and things up in Colorado and that tourist attraction over in England where they got 30 inches of rain in one day. Ground can't hold that stuff that quickly. It gets saturated. So that's that term. We're focusing on the amount of moisture that the atmosphere can hold. Next term. Term you're all familiar with. You've heard several times, I'm sure. Humidity. Very simply put, water vapor in the atmosphere or water vapor in the air. That's humidity. Is it humid today? Yeah, it's very humid today. It's been raining off and on. We're probably going to get rain again today. So the humidity or the water vapor in the air is fairly high. What's one characteristic about humidity? What's humidity usually do?
Flattens your hair.
Okay. Those girls just hate it when their hair goes flat, don't they? Other things? Go outside, and would you rather be outside working in the yard on a day that's 90 degrees and very humid, or a day that's 90 degrees and not very humid? Okay. Gets sticky, muggy, it's not very comfortable. You sweat usually a lot more easily on humid days because there's a lot more moisture in the air. Next one. Term that you should see on the news or hear on a regular basis, relative humidity. The measure of the amount of water vapor actually in the air compared with the maximum amount that the air can hold at a certain temperature. Measure of the amount of water vapor actually in the air compared with the maximum that the air can hold at a certain temperature. Now, when you look at air, this is the property we need to discuss. Air is made of gas molecules, whether that's oxygen or carbon dioxide or nitrogen. There are many gases you can put in there. What you have to know is about the particles in the air or the molecules in the air at different temperatures. Example is this. Doing dishes. What water usually works better to clean dishes with? Cold water or hot water? Why does hot water work better than cold water? What's happening to those water molecules in hot water versus cold water? Has to do with speed. What?
Faster.
They move faster. They're moving faster. So they're more active to get whatever you're trying to get off that plate or to get it clean. If you take two sets of water molecules, one moving very slow, one moving very quickly, the ones moving quickly have more space between the molecules. The cold ones are usually kind of bunched up. The warm ones are just all over the place. And they've got all this space between them. Now, if you look at air molecules, they're the same way. The warmer the air, the faster those air molecules are moving, and the more space there is between the air molecules. If there's more space between the air molecules, what does that mean that you can put in those spaces? Adam?
Oh, water vapor.
Water vapor. Right. The warmer the air, the more space it has to store water vapor. Air that is 90 degrees can hold a lot more water vapor than air that is 50 degrees because there's more space between the particles. Now, with relative humidity, what this is telling us is we're measuring how much moisture is in the air at that time compared to how much that air could really hold. Example, if I have this is my box of air, okay? And this box of air is 80 degrees. And I have a little chart that some weather guy has told me that in this chart, or on this chart, it says that if I have this box of air at 80 degrees, it will hold 10 milliliters of water. At 80 degrees, this box will hold 10 milliliters of water. Now, and I measure, and I find out that there are only 5 milliliters of water in this box of air that I've got. What is the percentage of the relative humidity? What's that? Why is it 50? Okay. It can hold 10 milliliters total. And currently the air is holding 5 milliliters total. That's half. 1/2, 50%. That's relative humidity. Weatherman has nifty little devices to determine relative humidity. They know, depending on what the temperature is, how much air or how much water vapor the air can hold, how much is actually in it, and that's relative humidity. The device they use is called a psychrometer. Now, this is basically a simple version of a psychrometer. This is one I whipped up yesterday. It's very simple. All it's got, 2 thermometers. These thermometers are exactly the same. They both read in Celsius. I just took them and mounted them to a piece of, like a file folder. 2 pieces of foam, cut little notches in it, ran them across there. What's the main difference between the two, though, is this. On one part of the thermometer, I took a bunch of this filter wool, or cotton basically, and wrapped it around there, and then connected it with some rubber bands. These are called the bulbs of the thermometer, the silver parts down here on the bottom. What they do to measure relative humidity is they take these two, and they take this bulb here, and they get it wet. This is the wet bulb. This is the dry bulb. This one stays dry. They read the two. They will come up with different temperature readings. Then you do a little formula, which is really easy. I'll show you in just a bit. And you come up with the relative humidity, or actually what the humidity is in the air compared to how much it can actually hold. That's a psychrometer. And we'll look at that a little bit more in a bit. Next one, absolute humidity. This is pretty simple. Basically, it's the measure of the amount of water vapor that's in the air at a certain time. Or I guess it says up there, measure the amount of water vapor that the air contains at any given time and place. So that's a measure of how much moisture is in the air. This is not concerned with temperature. This is not concerned with how much water or water vapor that air can hold at that time. But just at that point, how much moisture or water vapor is currently trapped in the atmosphere. That's absolute humidity. Difference between absolute and relative humidity. To determine relative humidity, you have to know the temperature. You have to know how much moisture can actually be held in that air at that point. And then you have to have a psychrometer or something to tell what the current rate of evaporation is, what the temperature, and then what the regular temperature is. Got this? Questions so far that you have? None? Okay. We got just 1 or 2 more. Here we go. Psychrometer. That's what I just showed you. Tool used to measure relative humidity. And it's composed of a wet and a dry bulb thermometer. It's not very difficult to make a wet bulb thermometer. Wrap a piece of cotton around it, dip it in some water, presto, changeo, wet bulb thermometer. We actually have 2 more vocabulary words after this. Next one, dew point. This is the one that Curtis was talking about when he gave us an example of condensation. You're looking at the temperature at which condensation occurs. If the dew point is below 0 degrees Celsius, then you have frost. I was watching the news last night. They said the low last night was supposed to be like 60 or 66 degrees, and the dew point was 48. That meant that if it got down to 48 degrees or 47 degrees or whatever last night, and I went tiptoeing through the tulips this morning, I would have gotten my shoes wet or my toes or whatever. That's the dew point. In Fahrenheit, what's the same thing as 0 degrees Celsius? 0 degrees Celsius is what in Fahrenheit? Tom?
32.
32, or freezing. 32 degrees Fahrenheit, 0 degrees Celsius. If you have the dew point, or you have dew occur and it drops below freezing, 0 degrees Celsius or 32 degrees Fahrenheit, then you take those molecules of water vapor in the atmosphere and you freeze them. And then they accumulate as frost. So you have to scrape your windows in the morning, or there's very good possibility we might get another frost. We're getting to the point where we might be past it, but I wouldn't be surprised if the temperature drops real cool. Maybe next week, one night, and kills everybody's plants that they've recently put down. Okay? That's a frost.